So, I'm Mathieu Lecomte, and I will talk about this paper, about this work that we did with my supervisors. So, in the title, you don't see, in fact, the name of a very important object in this paper, which is capacitated matching. So, it's an object on graphs. And I will try to motivate the study of this object using two applications, namely cuckoo hashing and load balancing in the content distribution network. And to study these objects, we will use belief propagations, which are message passing algorithm coming from statistical physics. But so first of all, I should introduce to you what is this object that we study. So what is a capacitated matching? It's so if you know what is a matching, it's a slight generalization of a matching, but I'll recall what it is anyway. So given a bipartite graph with the vertex and edge constraints, so here I put vertex constraints in red, and for simplicity we'll use edge constraints equal to 1. A capacitated matching is just a weight allocation on the edges such that we don't violate the capacity constraint. So for example, here if you put weight 1 on the edges in red, so basically you select a subset of the edges, you see that you don't have more than, for example, more than 2 edges selected next to this vertex, so you don't exceed its capacity constraint. So basically this is what is a capacitated matching. So as I said, I will try to explain why we study this object using these two applications, and then I will talk about how we study them. So the first application is basically related to content distribution, or you can think of VOD, for example. So currently, the way we distribute content is basically that the users are requesting for a content which is downloaded from a data center, which may be more or less distributed. Maybe there are caches somewhere in the network. But basically, you download it from a data center that the provider of the service needs to pay for, and it needs to dimension it, and it needs to be able to serve all the requests that the users are going to generate. So it needs to be quite big to store all the contents. It needs to have a high upload capacity, for example. But in fact, we are proposing to just, for example, store contents locally at the users' places. So, for example, using their gateways. And we can, before trying to just go to the data center, we could check if we can download these contents just from the users' gateways. So that would save quite some cost on the data center because you could make it much smaller. Maybe it would also provide higher availability of the contents. So if you want to design such a system, you have to answer some questions. For example, you have a lot of contents. Which one should you replicate? Which one should you store? How many copies should you store for each of these contents? And then another question, well, once you get requests for the content, you have a lot of gateways from which you could download them. So which one should you choose? And of course, the metric that you want to use to decide how you organize this system is what is the load reduction that you get on the data center. At least that's the one we use in this work. So basically, you want to make the data center as small as possible and as costless as possible. So this system, we can model it to some extent using a bipartite graph. So here is my bipartite graph. I have the servers on one side. I have the contents on the other one. And I put an edge between a server and a content if the server is storing the particular content, meaning that it is able to serve requests for that content. So here, for simplicity, I just put a cache size at each server of 3 contents, let's say. So I have 3 edges going out of every server. And so I said I would study capacitated matching, so I need to have capacities also. So here for simplicity for this talk, I will say that the gateways are able to upload one content at a time. That is, they have very limited service capabilities. And then I can say that the edge capacity is also 1, because anyway the vertex capacity here is 1. And for a content, what is the capacity? It is going to be the current number of requests that I have for this content. Meaning that if I have one request, I will just pick one gateway and say that this gateway is serving this request, and I don't need to pick more gateways. And then you can see very easily that if at one time instant I am serving those requests or using some of these gateways, the number of requests that, the allocation of the request to server is simply a capacitated matching of the graph that I defined. And then if I want to know for a particular organization of this system, meaning a particular graph here and particular capacities, if I want to know what is the load reduction that I will have for the data center, that is not on this picture, it will just be the size of this capacitated matching that I have. So this is why we want to study the size of these objects. So I'll try to go quite quickly, but basically this system is very random, because I said that the capacity for the contents are the number of requests, but it is not something that we know in advance. We may have statistics, we may have statistics on that. We may know a priori distributions on the popularity of the contents, but we don't know for sure. So the capacity constraints are going to be random in our system. And moreover, we envision quite large systems with a lot of gateways, for example. So you can't really coordinate all these gateways very efficiently. So there will be some randomness in the way the contents are cached by the gateways. Basically, you can say how many replicas you want for a content, but you can't really specify very precisely which gateway is going to store the contents. So this means that the edges of the graph I showed you are going to be random. And in fact, if we make some statistical assumption, the random graphs that we will have will follow some known distributions. So we can study these random graphs using known techniques. But also you could consider systems where the way you decide which server is serving which request is also random. So you could have a lot of randomness. But here for this talk, I will just assume we use the maximum matching at any time. I will not tell you how we can do that, but it's possible. And our result in this context is that basically we are able to compute for a given way of replicating contents. We are able to compute the load reduction on the data center, and thus we can optimize over replication policies, and we can even get explicit expressions as the storage size grows in each server. I will switch very quickly to a second application, which is cuckoo hashing. So as the name doesn't tell, it's actually a problem of hash table. So you want to build a hash table, you have a certain number of items, you have a certain number of keys, and you want to assign a key to each item so that you can retrieve the items very efficiently. There's a family of hashing techniques that are called multiple hashing, where you just decide that a given item can be associated to any keys among a given set. And then when you want to retrieve the item, you just need to check all those keys. So you have deterministically a constant time for retrieving an item. And there's a particular way to implement this family of techniques, which is called cuckoo hashing, where basically when an item arrives, you check if the keys that are allowed for these items are free. If one is free, you just assign it. And if all of them are already assigned, you just kick the item that was assigned to that key, you reassign the key, and you reconsider the item that you kicked out. So if you do that iteratively, you can always manage to build a hash table, provided it's possible with the choices that you had. And the question in such a system is basically to know how many items can you handle if you have a certain number of keys. And the problem is that these choices are random, so you want to be able to specify a number of items such that you can find build a hash table with high probability. So there is some threshold here on the way the number of items and the number of keys grow together to infinity. And under this threshold, you can, with high probability, build a hash table. And so what we do in this context is that we compute these thresholds, basically.
Centralized or distributed?
I'm not sure exactly what you mean. The way you assign a key to the item is distributed, but it's iterative. It's distributed.
Okay, and how do you deal with the starvation?
I'm not very sure.
Out of an item?
And then you want to reassign it.
Yes.
And the question is, so you will reconsider the new item. And if you iterate this process, if you are under some threshold on the number of items and number of keys, you know that you will succeed ultimately. And there are people that worked on how fast you will succeed, so how long does it take to build this hash table using these techniques, but I don't really have time to enter in details right now. So I just try to tell a little bit about the techniques that we use. So, the principle is that we want to compute the size of a maximum capacitated matching in a graph. And we are working on random graphs with certain distributions that are known to converge in some sense as the size grows, as the size of the graph grows. And what happens is that as the graph grows, it looks more and more like a tree. A Galton-Watson tree, actually, if you know what it is. So for a start, we'll just look at what happens on finite trees. How would you compute the maximum size of a capacitated matching on a finite tree? So there is a very, here I put a tree with vertex capacities in red, and I will just choose edge capacities equal to 1. So there's a very simple and greedy algorithm on finite trees, which is the following. We just pick a root, and we'll start doing leaf removal. That is, we are picking dangling edges and including them into the capacitated matching. And once we've considered all the edges, we know that we have a maximum sized capacitated matching, so we know the size of a maximum capacitated matching. The problem is that this algorithm we can't use on infinite trees, for example, because there are infinite paths, and you can't do leaf removal on an infinite path because you don't know where to start. So, in fact, you can convert this kind of greedy algorithm into message passing algorithms that are fully distributed. And basically, the nodes are going to send messages to their neighbors saying if they want to include an edge in a maximum sized capacitated matching. So we are running the same, I'll show you just on the same finite tree how this algorithm runs. So we initiate all the messages at 0. And we apply local rules to update them. And at some point, they converge to a fixed point from which it is possible to recover the size of a maximum capacitated matching. But it's still not over because there might be multiple fixed points to this algorithm in graph cycles or in infinite trees, and we need to identify which one is the correct one. Sometimes there are even no fixed points. And furthermore, we need to deal with convergence of this algorithm, convergence at the size of the graph increase. And for that, we use a second message passing algorithm, so this one comes from statistical physics. It's called belief propagation. Basically, instead of just considering the maximum matchings, we are going to consider all the matchings, but we are going to weight them according to their size, so that we can then, so we are going to use this kind of distribution that is a Gibbs distribution, where the probability of having a particular matching is proportional to some parameter to the power the size of this matching. So when we increase this parameter, we let it tend to infinity. This distribution concentrates on maximum sized matchings, and hence we can recover again the maximum size of matchings. And so what we do in very short, how much time do I have?
Half of a minute.
Okay, so in very, very short, we use this message passing algorithm from statistical physics to estimate the marginals of this distribution. So just a message for this algorithm is a distribution. So we need to choose an appropriate stochastic order to be able to establish convergence properties. And then when we take the limit as this parameter z increases to infinity, we are able to identify which fixed point of the first message passing algorithm is going to be selected. Because here, for this message passing algorithm, there's a unique fixed point, so it's always the right one, basically. And we can identify in the limit which one is of the first algorithm is the right one. So the scheme that we follow is basically this one. We would want to get the convergence of this quantity, the maximum size of a matching in the random graph, as the size of the graph tends to infinity. But we introduce what they call a temperature parameter. And we know we have this convergence property, and that for this finite temperature quantity, we establish the convergence as the size of the graph tends to infinity, and then we take the limit as the temperature parameters goes to infinity. So that was in very, very short. So if you have more questions, you can ask me. So just to conclude, what we work on is we compute the size of maximum capacitated matching in random graphs, for some random graphs models with some properties. And we also compute some associated phase transitions. And this allows to compute performance evaluation for this first system I talked about, this distributed content delivery network. And in particular, it allows to optimize its organization and dimension the residual data center. And we also compute cuckoo hashing thresholds, which allow, again, dimensioning of hash tables. Thank you.
We have time for one question. Everyone is very hungry.
Yeah.
Thank you very much.